Welcome to this last class. So here I will give you a recent example which was done by my student Dr. Akshat, and he has performed a correlative analysis on CMX4 alloy. This is a multi-component alloy which is having a more than 10 components, and these are used as a turbine blade applications in a single crystal form, and it contains a large amount of rhenium. It's around 3 weight percentage, and the main task is to reduce the rhenium contents without affecting the properties. So to identify that, we need to understand that what the rhenium actually doing during the high temperature creep deformation. Okay, so uh, he has performed correlative analysis of this alloy crept at different stress and temperature, and on the defects which are produced. Based on that, we have identified solutes which can which can replace the rhenium by almost 50% without degrading the properties. Okay, then just I will go through this work, and I hope that you will understand the crux how the atom probe tomography and the electron microscopy can be used to actually for the better alloy design for high temperature applications.
So, if you see the as-cast microstructure, we have a interdendritic region, okay, typical interdendritic region, and the interdendritic region, and there is a dendritic region, okay. And interdendritic region usually we will found as a nickel, aluminum, and titanium, where in the dendrites we usually see that rhenium, tungsten, moly, and cobalt and chromium are partitioned. Okay, so this is the typical distribution of solutes which we usually see in these alloys in the as-cast form. Okay, so to remove these dendrites, it is a very difficult because these are very slow diffusing solutes. So usually the DRDO labs, what we do they do the step heat treatment. Okay, where these solutes or any segregations which are present can be removed with subsequently. Overall, after aging, you will get a microstructure which is having a very nice cuboidal shape gamma prime and the gamma phase. Okay, so here there is a diffraction pattern where you can see that there are superlattice ordered spots. Okay, which shows that these are all ordered structure, L1 to ordered structure. If you take atom probe data across the interface between the gamma and gamma prime, these red color atoms are rhenium, these golden color atoms are nickel. If you take the composition profile, actually you can measure the partitioning at atomic scale. Okay, so usually cobalt, chromium, rhenium, tungsten, and moly goes to the gamma phase, while aluminum, titanium, tantalum, nickel, and titanium goes to the gamma prime. So typically we tell these solutes are the gamma prime stabilizers. This compositional partitioning is very important and is very crucial during creep deformation. Based on the partitioning, these solutes can pin the dislocation moment. Okay, so they can as a drag force while the dislocation shears the gamma prime. So I'll come in detail about these mechanisms. Okay, so as I told about the mechanism, you can see that a typical superalloy has a L12 structure. These are all 100 planes, and your triple plane, if you see in the perpendicular to the plane projection, you can see these are the mixed atoms. Okay, if we call this as a, then above this A, there will be another layer. There is a third layer which we tell it as a sequence of A, B, and C. And this ABC sequence repeats. And this is a typical FCC or the L1 to FCC based sequence, which we observe if you see the edge-on condition of the triple one plane. Okay, so now these superalloys with this structure, if you deform it at different temperatures and stress levels, different deformation mechanisms comes into play. Okay, so here I am just showing you an example where it's a two-dimensional projection of gamma prime with the triple one plane, and there is a soft gamma matrix. And here I am showing you a low temperature, intermediate temperature, and very high temperatures. Correct. Now, if you deform the microstructure, at low stress and low temperature, the gamma is a soft matrix. So you will produce the dislocations of the type of half 101. These are perfect dislocations for FCC. They actually, at these stress levels, very low stress and low temperature, they actually get pinned at the interface. As I told you before, these interfaces are coherent and there is a strain. Okay. And these dislocations at these stress and temperature level cannot shear the gamma prime. Okay. So they get accumulated and they restricted at the gamma prime interfaces. If you go to high temperature and low stress levels, due to the high temperature, they these dislocations can actually shear the gamma prime along a by 2 101 direction. And this a by 2 101 in the gamma prime is called superpartial dislocations. Correct? And this creates an antiphase boundaries. Now, while moving along this 101, you can see that there are they came up with the creation of wrong aluminum bonds. Fine. Due to these wrong aluminum bonds, they are usually high energy. Okay. And due to this high energy, they are not stable. Okay. Typically, these antiphase boundaries are disordered structure. Okay, inside the gamma prime, which are ordered structures. So this is a high resolution image where you can see a typical antiphase boundary. Okay, remember these are high energy with the aluminum wrong bonds. Okay, now if you go to a little bit of higher temperature at intermediate temperature and intermediate stress levels or high stress levels, these dislocations at the interface actually can shear the gamma prime with a by 3211 dislocation. Okay, so what will happen by sharing this dislocation? They form an intrinsic stacking fault. Remember, these are low energy. It means that the nearest wrong neighbor violation did not happen. Okay, that's why these are low energy intrinsic stacking faults. Okay, typically, if you see a microstructure where you can see that these bright lines corresponds to this intrinsic stacking faults. At high resolution, it shows a structure which is an HCP based, which are typically DO19 based, and intrinsic stacking fault means it is like a removal of an extra triple one plane, which we see in the adjoint condition. Fine. So this is a low energy intrinsic stacking fault. There is another case exists when the stresses are enough that the two consecutive triple one planes, the A by 6112 dislocation can shear the gamma prime, due to which it forms a complex stacking fault with the wrong nearest neighbors. Due to these wrong nearest neighbors, it has a very high energy, okay, but less than the antiphase boundary energy. This high energy can lead to the complex stacking fault to convert to the extrinsic stacking fault by a reordering step, which was proposed by Kolbe long before in 1970s. Okay, and this formation of extrinsic stacking fault usually acts as embryo for micro-tuning mechanism. Okay, so during creep deformation, usually what will happen, the creep strain can be accumulated by the formation of extrinsic stacking faults and micro-tuning, and also the intrinsic stacking faults. Right. So now with this introduction, I will just briefly come back to the unit cell where I told about ideally it is a Ni3Al, correct? Aluminum occupying the 000 positions and nickel occupying the uh, half zero positions. Now, if you see the generations, which are generation of superalloys which were developed from early 1970s to 2000s, the first generation doesn't have any rare earth additions or the any high density elements. Mostly these are concentrated to aluminum, chromium, cobalt, tungsten, titanium, and tantalum. So, but the creep properties of these alloys were very low, even though the densities are lower, around between 7.8 to 8.1. So in the second and third generation, there is a significant addition of rhenium by 3 weight percentage and 6 weight percentage. Even though the creep properties have been increased 2 to 3 fold, but the density of these alloys have become more than 9 grams. So typically now fourth generation super alloys, they have a density is about 9.4 to 9.6 gram per cc. Okay, so it has increased the weight of the blades. And one more important point is rhenium and ruthenium. These are all very costly elements. Okay, so these have approximately around $10,000 per kilogram. Okay, and with respect to tantalum and tungsten, these are almost 10 to 20 times costlier. Fine. So with this background, uh, what I want to say is, if you see a multi-component alloy, you cannot treat it as a idle Ni3Al. In a multi-component alloy, some of the solutes goes to the aluminum sides, some of the solutes goes to the half of zero sides. So you will have a mixed number of atoms which are actually stable at 0, 0 positions, but there are some atoms which are stable at the half of zero positions. Okay, this has to be remembered because in the later stage, we see that how this is important to understand the coal-based mechanism. Okay, and one more important point which I want to convey is the complex stacking fault, which I told about the dislocations passing across the triple one plane in consecutive triple one planes. Okay, here if you see that if there is a pure unit cell, the CSF energy is around 195 to 275. But if you have a mixed unit cell, such as tungsten and tantalum occupying the 0, 0, 0 positions, then your complex tank fault energy increases by almost 2 to 3 fold. Okay, this will have a direct consequence on the mechanism, deformation mechanism, which will happen at during creep of these alloys. Okay, so with this, I just introduced that the experiments which my student Akshat has carried out is the correlative use of tomography and the electron microscopy to understand the solute defect interactions. These defects are interfacial dislocations, stacking faults, microtwins, and antiphase boundaries. Okay, and this led to the understanding of creep rate limiting solutes, which are other than rhenium. Now, based on this, we also generated diffusion mechanisms which are unknown till now about before this work done. Okay, as I told you, we have used extensively the electron channeling contrast imaging in SCM to identify the defects at the macro scale. Then we performed sample preparation from those locations. We confirmed in by using the high resolution electron microscopy in TM, and subsequently the same samples we performed the chemical analysis locally at atomic scale by using atom probe. Okay, so if you see the creep deformation, I have divided into two important parts. One is intermediate temperature and one is high temperature. First, I will talk about the intermediate temperature. Okay, so at intermediate temperature, you can see that after the creep at 800 degrees Celsius and 800 MPa, you can see that in this gamma gamma prime structure, the gamma prime the interfaces are serrated. But you see that we don't see any contrast related to the faults. Actually, we should see it. Okay, so what we did is we went to Bragg's condition in a two beam condition, and at that particular condition 002 bar, by using electron channeling contrast, we can see that these appearance of bright lines exactly at the same location, which are indication of shearing of these gamma prime precipitates. Okay, and with the stereographic projection, we identified that these are corresponds to 1 bar plane. Okay, along which the shearing of gamma prime has taken place. Fine. So we have identified at a macro scale, and also at certain locations, we see the creep strain is accumulated by the formation of multiple microtwigs. In one way, we also got evidence that these extrinsic stacking faults, which are very thin here, are converted towards the twin during the creep. Okay, so this is the evidence that how these extrinsic faults are converting to the twin. They are acts as an embryo. Right? So now what Akshat has done is he has macro scale, he has identified those faults. He has made an in-plane lift-out method, atom probe tip, where you can see this is a bright field image. You can see these dark regions, okay? And this particular region, he has identified that these are all extrinsic stacking faults. Right? Now, the same atom probe tip, what he has done is he performed the tomography where he has identified the stacking fault by plotting chromium 3.2 atom percentage isosurface. Okay, if you take a composition profile, he what we see is there is a enrichment of chromium, enrichment of cobalt, while depletion of nickel and depletion of aluminum. We don't see any significant composition fluctuation of other solutes. What he has done is, then again, he has plotted a two-dimensional profile perpendicular to the viewing direction. And what we observed is there is a aluminum depleted region across the fault plane, while there is an aluminum rich region across the fault plane. So there is a variation in aluminum composition. Similarly, the nickel also varies. So wherever the aluminum is depleted, there nickel is enriched and tantalum is enriched. Wherever aluminum is enriched, there nickel and tantalum got depleted. Okay, so similarly, what he has done is he has performed a correlative analysis of a region where he has obtained the twins across the tip. Okay, and this is a typical diffraction pattern on the atom probe tip where there are twinning spots, and he has taken a dark field from 002 bar where he has shown that these bright regions corresponds to the twin boundaries, and we have identified it as a T1 and T2. Same atom probe tip, he did perform the atom probe for the chemistry, and you can see this gamma gamma prime interface. This is exactly at the top, and these planar interfaces are reconstructed with two different isosurface values. Okay, and this planar interface corresponds to the twin boundaries of one particular twin, and these were marked as T1A and T1B. If you take a profile perpendicular to these regions, at these two regions, we see that along the twin boundary, there is a variation in composition. At certain location, there is an enrichment of nickel. At certain location, there is a depletion of nickel. Wherever there is a nickel enrichment, aluminum is depleted and tantalum and tungsten is enriched. Wherever the nickel is depleted, aluminum is enriched, while the tungsten and tantalum and cobalt get depleted, while the chromium is enriched. So this behavior was not seen before in these typical alloys, why the variation in composition is taking place along the twin boundaries. Okay, for more understanding, what he has done is he has plotted a two-dimensional composition map of aluminum across these twin boundaries perpendicular to the viewing direction, and you can see that the aluminum concentration at this region is less, and while going towards this direction it increases. Correct. Now he has plotted a composition profile across this twinning plane, and what he has observed is from X to Y there is a continuous decrease of aluminum composition, while there is a uh, continuous increase of aluminum composition and continuous decrease of nickel composition. Okay, with these profiles, we need to remember that as per the Kolbe's mechanism, he has proposed in a ideal Ni3L lattice. Correct? Either ideal Ni3L lattice means only aluminum is occupying the 000 positions, while nickel occupying the FCC position. So he has assumed Ni3L lattice. So based on Kolbe's mechanism, the formation of extrinsic stacking fault by shearing along 112 bar direction in two consecutive planes will lead to high energy CSF. Okay, so this creates a aluminum high energy bonds. These aluminum high energy bonds will reshuffle to form nickel aluminum bonds, which converts the high energy complex stacking fault to a superlattice extrinsic stacking fault. This particular extrinsic fault has a DO24 structure, which is an HCP based structure. Okay, this has to be remembered now. And this particular extrinsic stacking fault, while shearing of 112 dislocations along consecutive planes, it will convert to the twinning. Okay, so this is how Kolbe has proposed that from extrinsic stacking fault, from complex stacking fault towards the extrinsic stacking fault, and how the tuning is taking place while accumulating the creep strain. Now coming to in our multi-component alloy, as I told you, ideally these are multi-component, and aluminum sites are occupied not only by only with aluminum, these tungsten and tantalum also can occupy these 000 positions. Okay, due to this composition, multi-component nature, what we propose is that if you remember in previously, I also talked about the CSF energies. If there is a tungsten in the alloy in Ni3Al, the CSF energy is much higher as compared to the ideal Ni3Al. Similarly for the tantalum. Okay, so based on this data, what we propose is, if you have a Ni3Al tungsten tantalum gamma prime lattice, and if a dislocation shears the gamma prime, okay, you can see shearing of the gamma prime along the 112 bar direction, then you will create a high energy aluminum tungsten aluminum tantalum bonds, which is different from aluminum aluminum bonds, and these have much higher energy than the Ni3, which are aluminum aluminum bonds. Fine. Now what we propose is that there is an additional step which is happening of reordering, where the aluminum tungsten tantalum bonds are replaced by aluminum aluminum bonds to get a low energy CSF. After getting low energy CSF, as these are also uh, wrong nearest neighbors, which is having a higher energy, these will convert to a NIL, forming a extrinsic stacking fault. As I told you, these extrinsic stacking faults has a locally DO24 HCP based structures. So tungsten and tantalum prefers to occupy these HCP based structure because in the phase diagram, they have an equilibrium structure of CO3W or CO3T. So they want to reside on HCP based structure. Then they will segregate back to the tungsten to these extrinsic stacking fault, and with this the deformation proceeds by tuning process. That's why you will get a aluminum depleted region, aluminum enriched region, and whatever the atom probe tomogram has able to capture it, it is at the intermediate stage where these composition fluctuations are going to happen. Fine. So this is how we have modified the coal-based mechanism by an additional reordering step, which is an aluminum low energy CSF formation from aluminum, tungsten, and tantalum. Okay. So this I talked about the intermediate temperature. Now, if you go for high temperature at 1000 degrees Celsius, which they have a nearest neighbor violation and higher energy, these during after creep deformation, you can see that these gamma prime precipitates have been sheared by these antiphase boundaries. Antiphase boundaries. Okay. And even at the gamma gamma prime interfaces, we see a large amount of dislocation network. Okay. These antiphase boundaries typically they are bent if you observe in the cubic 001 directions. Okay. And if you clearly see in Hadoop STEM image, you can see there is a significant change in the Z contrast across these anti-phase boundaries. If you take high resolution microscopy, these anti-phase boundaries are actually a disordered gamma phase of a structure. Correct? The FFT is shown from APB and gamma prime. You can easily see that these are disordered structure. If you take a composition profile in TM, you can see that actually we see a slight enrichment of rhenium along these antiphase boundaries. So what Akshat did is he has performed tomography at the interfaces, and at the interfaces he has located these interface grooves which corresponds to the interfacial dislocations. Okay, and if you take the composition profile across these groups, you can see there is a enrichment of rhenium, enrichment of moly, and also the tungsten at the interface. This shows that if this particular dislocation, if you get enough time, it can shear the gamma prime, and these rhenium, moly, and tungsten, it might possible that they drag this dislocation. Based on this, what we got is we able to capture an antiphase boundaries in the atom probe, where this is the planar feature. And if you take the composition profile across this planar feature, what we see that the moly, rhenium, and tungsten, which we have seen at the interface, were significantly segregated along this APB plane. It shows that during creep deformation high temperature, along with the rhenium, moly, tungsten, and hafnium and plays a very important role. Interestingly, if you take the hafnium profile, usually now hafnium is in the alloy is around 0.1 to 0.2%, and nowadays in the latest generation of alloys, the hafnium content has increased up to 0.3. So the literature doesn't talk about hafnium, but it was shown that the creep properties are enhanced by the addition of hafnium. So this time we have shown that for the first time that actually by hafnium actually drags the dislocation during the formation of APB antiphase boundaries while shedding the gamma prime precipitates. So this shows that the hafnium plays a very crucial role in high temperature creep deformation. Okay, so based on these two data sets, which are at the intermediate temperature and the high temperature, we got to know that at intermediate temperature, the creep rate limiting solutes are tungsten and tantalum. Okay, and at high temperature, the creep rate limiting steps are tungsten, moly, and hafnium, other than rhenium. Okay, whether we can do the alloy design based on these solute segregation phenomena which is happening. So the next part was to explore how we can modify the composition of CMX4 by replacing the rhenium with the segregating solutes. It is expected that by reducing the rhenium, definitely the creep properties will deteriorate. But based on this, my two students, Shashi and Poonam, what they did is they designed two alloys, CMX4W, CMX4WT. Okay, and here there are the creep plots, which shows the difference in the creep with time. Okay, this is the creep strain and this is the time. As you see that for the CMX4 base alloy, the within 10 hours, the creep strain went to 3% and the sample got fractured. It means the creep rate is very high for this particular ideal CMX4 alloy, polycrystalline alloy. Okay, but with the addition of the tungsten CMX4W, which is a B1 alloy, the creep rife has increased up to 40 hours, and also the creep strain increased up to 5% with a less creep rate. Correct? Now, if you add tungsten and tantalum with the replacement of rhenium by 1.58 percentage, the B2 alloy, it did not fail fractured until 145 hours. And even it shows only the 3% strain without fracturing. So this shows that how how the compositional analysis across the defect features can be used to fine-tune the composition to reach a composition where with the reduced rhenium content, we can actually reach a good creep properties. Okay. So these alloys now we have the detailed microscopy and tomography is going on these particular alloys, which will be published soon. Okay, so with this, I will end my talk, and I have shown how an atom probe tomography can be used to understand the solute defect interactions and how the deformation mechanisms can be revealed. I have shown that we have proposed a modified pole-based mechanism by introducing an additional step of reordering during creep at intermediate temperature. And also, based on the segregation behavior, we have reduced the rhenium content by almost 1.58 percentage. Okay, and we can come up with a composition uh, as per the solute segregation behavior with improved creep properties.
I hope that you have understand this last lecture where Akshat has shown that how we can replace the rhenium with tantalum and tungsten, with higher amount of tungsten and tantalum to get better creep properties without affecting with lower density, with lower mass density and cost. Okay, and this is the last class. I hope all the students or the faculty or the industry experts who have listened to these lectures have got a basic idea about the use of atom probe tomography. And I have not gone detail in electron microscopy basics and also scanning electron microscopy because okay, I hope now you understand what Akshat has proposed. Okay, so I hope you have understood the basic crux of this work, where we have replaced the tungsten rhenium with the tungsten and tantalum, and the main thing is to use of atom probe tomography and the electron microscopy to get the structure and chemistry of these defects and how these defects are correlated with the diffusivity of these solutes. So this is the last class, and I hope all the students, faculty, and the industry experts who are attending have enjoyed this course. And I hope you got a feeling that how these techniques can be used in a correlative way to understand better mechanisms, especially in the metallurgy and structural materials. These have a huge implications on semiconductor industries, even though I have not covered some examples because there are several works, correlative works, which are very important to understand the semiconductors, the especially the interfaces. Okay, I with this I will end this course now, and I thank NPTL to give a very great platform where this course was executed successfully. We have given also the brief introduction practicals to the sample loading in the atom probe tomography and also the FIP preparation, which is a very crucial uh, for any student who are using FIPS for the sample preparation. Okay, so with this, I'll thank you all for listening me throughout this course, and goodbye.